it may not be seen in my screen, but it's recording. Yeah, so yeah, let's go ahead. So if you have any queries or anything, you please interrupt us. Fine. So what we'll do is, for starting part, let us take like few minutes just overviewing the tool, and then we'll draw a simple example, like simple circuit file, mainly an RLC circuit or maybe a very simple circuit, dynamic circuit. You can we will just do an hands-on on that simple circuit, and having done that for a few minutes, we'll go for the in the demonstration mode. So will just show you the assignment problems, mainly the transmission line and how the things are modeled inside a commercial package, and so on and so forth. Yeah. So yeah, so let me just start with this installation part. I hope you can see the screen. Yeah.
Yes, yes.
Yeah.
Okay.
So to install, actually, I hope you had followed. So I should not. Do you want me to quickly go through the steps of installation, or I think it should be easy, isn't it? Yeah, I think, yeah, let me just browse through. So you, the package is passed to you, and I think it will install appropriately in the C drive, like default path, if you have done so. And then you have to do this kind of settings here. So these are some batch files you need, like some files, let's not worry what it is. So these are executables of ATP, so you need to just assign that. Yeah. So having done this setting, so these are like plotting things. So when you have a result, so which tool you want to use it to view the result. So we are using plot xy or something like that. Yeah. So this was the so the package, the core package, trapezoidal method, and every package for uh, elements are actually pertaining to 5.7th version. Fine. So this is the yeah, 5.7 is actually the version of the preprocessor. Fine. So let me just clear it here itself. There is a package called ATP, which we refer to as EMTP ATP. Where it went? Yeah, I think I didn't include it here, but it's mainly called as ATP, alternate transient program. Yeah. So EMTP ATP. So that is the package main executables which solves a circuit. Yeah. So originally these were like a textual kind of thing. So you write a code in a text and then pass it to this executable ATP, and it gives you a result. But this ATPDraw, when you say draw, it's a preprocessor, in the sense it's like a paint tool wherein you just draw a circuit, but the simulation is done behind in the ATP. Yeah. So that is the main idea. So wherever you search for ATPDraw, actually it's mainly referred as a preprocessor. Fine. So in the 5.7th version, there is also a preprocessor passed with the passed to you via Moodle, but this has some limitations in the UI. Actually, I may not. Let's not invest time on that. But instead, I'll ask you to refer to this package version, which is the latest one, 7.2, and it's very uh, what do you say, like soothing to look in the circuit diagram, and lot of controls in sideways. Yeah. Actually, you can do the same thing there, but there are some more modifications and some more advanced tools like metering, then plotting and reading a lot of files you can do with this new version 7.2. So it's just a preprocessor. Fine. So version of this won't change the solution, but this is the idea. Fine. And most of the things like the downloads and discussion over these tools and ATP functions will be easily available in this net. I think this is also passed, so you can just check on your time. And there was a license file actually, which license in this in an agreement file, which you need to just follow up. In this, you just need to sign in, and for an year they will grant you a license, student license. So I won't show you, we won't show you there here those things here, but you can just agree to it, and they will send you a message. Okay, you are now you have a license for student version, something like that. Yeah. And just to test the install, like we asked you to open a file which is already available in the example folder, and just to execute it instead of looking what elements these are, and maybe you can explore also, no limits to that, but just to test the functionality, we do this, and there is some functions to be done. We'll just explore what these things are, and having done that, at the end you get some kind of weird looking terminal and some GUI, and then the plots are obtained. So I hope till here things were pretty straightforward, isn't it? Yeah. Yeah, see, you please agree, if
Yes.
else I may not know. Yeah.
Yes, we have
Mhm.
installed it.
Yeah, yeah. So this was the things which were already passed to you, and there you already did some process. Actually, you sub process, make ATP, blah blah. We'll see that what these things are. So the idea is actually once you install all these elements, at the end you will have this icon like coming in your desktop. You just need to open this and you will have this kind of GUI appearing. Yeah, it's taking some time to start. Yeah, so this is the GUI. So what we'll do is I'll just take few minutes to explain you the controls and what things are located where and so on and so forth. So the moment you open this, you can directly go to help and look in the about section. So it just states about which version it is. So it is just, I think 2 months back. This version was launched 2 months back, 2020. Fine. So these are some settings, like simulation settings we'll be doing, and there are a lot of different simulation study altogether you can do. So first is time domain simulations, frequency scan, and harmonic injections. All those things we'll see sometime later. So let me just clarify this, like just put the idea now itself. Like this session will be just the basic overview on how to use the functionalities, and maybe later if you want to explore some advanced tools like this or maybe some more elements, we'll on interest we'll take it again. Yeah, so these are some settings, and maybe by wording this may look somewhat familiar. It's saying delta t, so it corresponds to step size, some maximum time, some x opt, c opt. Let's not worry what it is. We'll clear it now after a few minutes. Then some frequency terms. Yeah, and if you go to selection here, actually you have a lot of elements coming up. So maybe in case if you can't see this dialog, actually this left hand side, you can go to view, and then you can just check mark this sidebar. So maybe let me just show you. So if you have screen like this, you can go to view and then just select sidebar. And in fact this is also, it also hold in the ATP 5.7 version, which is passed. Yeah, so yeah, so there a lot of elements are available here. So let me just open example, like a file wherein all the elements are available. Let me just show you that. Yeah, there is a file. So yeah, I hope you can see this. So these are some minimal files, or in the sense the files which are already passed to you in the ATP module, and these are some interfaces actually. The elements and their interfaces. So a lot of things are available, like probing thing for single phase and three phase. So mainly these are metering terminologies, voltages, currents, then some kind of transposition or swapping elements, and some connections. We'll see each and everything, mostly everything. And branch are elements which connect two or more nodes. So registers, basic elements, RLCs, then polyphase. So if you just observe, actually if you have a single node, actually this pertains to a like a thinner line, it pertains to a single phase entity. But if it is thick, it implies polyphase entity. In the sense, it may be two phase or 26 phase or so on and so forth. Fine. So there are some elements like corresponding to like capacitors and inductors, wherein you can pass initial conditions as well. For example, let me open it. So you can pass positive terminal voltage and negative, like potentials you can specify here. And for inductor, you can specify what is the initial current going. And though they have mentioned U0, I0, it doesn't mean that t equal to 0 only you need to start. But this just gives an indication, okay, initial value can be passed. But it can be passed at any time. Yeah. Then you have another nonlinear element. Maybe you can explore it or at your will. I'm just showing you the minimal element. In fact, you can always create a element to suit your project. Fine. So there are like synchronous machine here, then different models of induction machine, then transformer, lot of transformer elements are here. Fine. And then some kind of inbuilt like scripting tool called models. It's some language wherein you can, in this ATPDraw it's available, wherein you can write your own code. Fine. So we'll see all these things eventually. Yeah. So, and these are some steady state tools. Maybe if you want to do just a power flow, it will be overkill to do power flow using ATP, but yeah, maybe your solution requires or your project requires initial conditions to be calculated for a huge network. Fine. So this can be used, and to interface or to talk with another tools, maybe let's say Octave or Scilab, or if you want to include some other external model, you can use this kind of boxes. Yeah, we'll see what these things are. Yeah, so So this is the idea. So what we'll do is now, yeah, let me just show you some more stuffs. Let me just open that very same example which we asked you to try it out. So when you zoom it, and this is the center part, you can just align it to center. Then you can hit plus button, plus in your numerical tab to zoom in, minus to zoom out. Fine. Yeah, and then you see some kind of node somewhere, some it is red and somewhere it's black. So everything settings are here. We'll see one by one. So this is a simple circuit. Fine. So in fact this is like this. So if you just drag any element, you can add it again and so on and so forth. Yeah, and all textual elements also you can add just to signify a part. Yeah, and so let me just show you when we run what happens. So a general process is like, if you make the circuit for first time, it's always good to start with this. So you hit for sub process and then you say make ATP file. So the moment you do ATP file, it will ask you to save it somewhere. So let me just save it somewhere in the default folder. It's already there because I had tried this circuit, so it got saved, and then you can hit run ATP. Fine. So when you do that, it does some calculation, and actually the command terminal, what you see in the presentation here, I just switched it off because I don't want it. So you can just explore it on your will. So these are available in the view options. Fine. So and then this is an independent tool called plot xwin or plot xy tool, wherein you can select any signals. Fine, and then you can just plot it. So these are things which were already given. Fine. So just to explore things, let's construct a quick simple circuit, and maybe this circuit will do as a hands-on, so that you will get more clear picture. Yeah. So I hope you have screen. So idea is, actually I'll just show you a step. We'll wait for a few seconds and you just do it, or parallelly you can just shrink your size like this, the video session, the demo, the screen what you are seeing, you just shrink it at the side and you can do it here in parallel. Fine. And we'll take it very slowly. So we'll just patch a circuit, which is this circuit, a simple RLC circuit with a switch. Fine. AC source with some voltage, maybe some voltage, and this parameters. I hope you can see this, like 10 ohm, 63.32 millihenry, and then 10 microfarad, and so with some initial conditions. Fine. So let me just quickly patch this circuit. So how to begin? So let me just show you that. So first I'll just create this, like file new, or directly you can hit this new button. Yeah, any doubts in this till now? Yeah, I think it should be straightforward, isn't it? Yeah. Yeah, so to begin with, so in fact you can drag and drop from here. You can select any element from here, like a register, and you just paste it here. I think it's having some issue, or you can just, yeah, just a sec. Yeah, it's here. Just zoom in. So you can just do that dragging thing, or you can just click on that and it will appear. Actually, a lot of things are open in my system, so maybe it's giving some issue. So let me just close and start. Yeah. So now we'll just construct that. So instead of dragging from here, I'll just show you how to do it here. So when you right click here in the canvas, you will see all the very same elements here available. Fine. So let me just quickly place this register first and center align, and then hit plus button in my system. Fine. And then add, since we want to specify VC of 0, which is here, as 3 volt, I'll just pick a capacitor value wherein we can initialize the voltage. Fine. So let me just choose a capacitor wherein you can specify the initial voltage. Fine. To rotate it, I will use, like, you can rotate it using Control R. Fine. For timing, it should be straightforward. So let me rotate it and keep it here, and then an inductor. So I'll place an inductor. So I hope you can do it parallelly here. This should be straightforward, and we'll wait for some time for you to quickly pick up. Yeah, and then I'll ground this portion later. Yeah, so now we'll require an AC source. So we'll go to source, So various elements are there, so instead of explaining each and everything, eventually like you'll explore and you'll get the more clear picture of the elements, fine, components and things. So here I want an AC source, fine, of 50 Hertz. So I'll place it here and I'll press Ctrl R to rotate, and then I can place a switch, or let me just, yeah, any doubts? Okay, yeah. So when you place this for first time, it will give you a weird picture, but once you open it, it will prompt you to enter some value. So let's do that. So we want a voltage source, a single phase source, angle should be in degrees, and amplitude is line to ground we are specifying. So let me choose that as 10 volts, fine, to begin with. Frequency is 50 Hertz, phase is 0, we are saying. At start time it's -1, fine. So it's a very key thing here. So idea is when you say as -1, eventually the circuit is solved in steady state and it starts with your steady state kind of idea, yeah. But to have a transient, so idea is to mimic that circuit as like a AC source like running from infinite time, and then you have a switch and then this RLC circuit. But instead of that, I can imbibe that switching phenomena within the source here. So because it's very easy to do it here instead of choosing another switch element, fine, because it requires some more specifications. I'll show you that, fine. So what we do is actually when you specify, see, when it is -1, it will start with steady state. But instead of, if you want to make a transient happening, you can just specify a time, let's say 0.1, then it will start at 0.1. The source will start at 0.1, else it will be always 0, yeah. But since here we want to start at 0, we'll specify at 0. But just keep in mind, -1 will start with a steady state, but when you say 0, the source will start at t equal to 0, means a transient will be observed, fine. So that switching element we are imbibing within this source. Why we are doing this? Because it's very easy to assign, fine. We'll get to that source thing later. So it's 50 Hertz and angle, actually by default a wave, the waveform which is chosen as default as 0 degrees cos wave, fine, cos. So when you start at 0, actually it will, if you measure the voltage, it will start as a cos, fine, cos wave decaying. So it will start from 10 and then oscillate, yeah. If you want to make a sinusoidal source, you impart -90 or +90 here, yeah. Having done that, and we want this grounding thing, so we choose grounded, and then we say OK. The moment you hit OK, it will take its form, which is more commonly known to us, fine, and you can just join it. So just remember, this is actually a source plus the switch here. So since we are starting at t equal to 0, stop time we keep it 100 because we won't go to 100 at all, yeah. Now let's quickly assign value of R as 10 ohm, fine. And for example, if you want to require like what all data each block correspond to, you can always click help. So it's neatly written here. You can just check, okay, so only one resistance and 2 nodes are available for this, so that's it. And if you want to do some kind of measurement, you have options to choose here. But let's start with like no elements, like slow at start. So we'll just make everything as 0, like no measurement, nothing, okay. And then inductor, and there is some more elements to that, so let me just show you. So it gives you some weird formula like Kp also, like some factor, fine, let's not worry about it. It's just an inductor. And yeah, if you have noticed, actually in this simulation, yeah, let me just show you that first. So here you specify L equal to 1 ohm, fine. But for example, and this actually corresponds to some setting. If you observe in the help file, it says if x opt, like there is some variable somewhere, it says when it is 0, then it will be taken as millihenry. Else, if x opt you specify some number, it will take as an ohm. So let me just show you that what it means. So I just specified this as 63.3 millihenry. So it's already in millihenry, so 63.3, fine. So let me just show you that. So if you go to simulation, actually there is a variable called x opt, which corresponds to inductor frequency, and C opt means capacitor frequency. So when I say this as 50, let me just show you. So if I write 50 and click here, and if I go to inductor again, see, it will ask everything in ohms now, fine. And in case if I make it again 0, it will ask as millihenry, see, fine. So you need to notice, and whenever you are making a circuit appropriately, you need to set this. And why they have done this? Because this is required very much in some kind of simulations, yeah? So we set everything to default to begin with. So we are specifying inductor and capacitor, not reactances and like reactances, yeah. Any doubts or anything so far? Yeah, I hope I am audible, isn't it?
Yes.
Well, actually, I don't know when my network or thing are interrupted, so I just confirm. So please help me out, yeah. So same thing goes here. So if you set X opt as 50 or 100 hertz, so that pertaining to that frequency, you need to specify what is the ohm or reactance value, yeah. Yeah, so now we have set everything to DC, let's say 0. So you need to specify the exact value of that. Excuse me. So if you come to capacitor, you need to specify what is the capacitance value. So I guess it should be 10 microfarad. Let me just check the circuit again. So circuit, I just placed it here. Yeah, so it's 10 microfarad, 63.3 millihenry, and 3 volts initial voltage you will specify, and 50 hertz source. So let's not worry about peak. We are worried about the transient. Yeah. So let's do that. See, here we have a feature of inputting this plus and minus potentials. Actually, you can specify with respect to some arbitrary value, but here we'll fix it to, let's say we'll just make negative terminal to 0, and here you can specify as 3 volts. Fine. In fact, you can do this also. You can write 0 here and minus 3 volt. Both will correspond to same thing. Fine. So we are doing this, and this is 10 microfarad, and I will say okay. So this setting things are done, but still the circuit is not complete. If you look in the circuit, actually grounding is not there, so we need to add the ground. So unlike in other tool, most of the tool you will have ground also as a separate element. For example, if you just search in source or switch, you won't get ground anywhere. Yeah. So for actually here you have very good feature of having ground locally at every node. So you just need to invoke it. Fine. For example, if I want here, I'll just right click over this node, and you will get this kind of a block, which is very useful later. Let me mark you with this. It's very useful. This feature is very useful later. So I'll just select on ground. So it just grounds it. Just to suit the orientation of ground symbol, you can just click on this symbol also. Up, then it's left, then it's right, and then it's again bottom, something like that. Yeah. So I'll say okay. So it just gets grounded. Same thing you can do with any node. For example, here. Yeah. And in fact, this block will be using. I'll just show. We'll just come to that shortly. So I hope you are also performing the same thing with me. Yeah. So if you have any doubts, you can ask me. I hope if you build the circuit with me, it will be very helpful. Yeah. Yeah. So this is the thing. So yeah. Okay. So now we want to invoke some kind of measurements here. Fine. So let me just again, it's a matter of practice. Like, since you have made a circuit, let's save it and then impart something else. Yeah. So let me just save it. So what I'll do is I'll just save it somewhere in my known folder. So I'll go to E747, and I'll just impart some name. Let's say a simple example. So it just gets saved as simple example in this default drive. Yeah. So now what we'll do is we need to set some things. So first we'll set the circuit and then the simulation settings. So here value is assigned as 10 ohm. Here it's 63 point this, and it's 10 microfarad and 3 volts. So let's specify the currents and voltages. So if you want, you can always specify a current. Since it's a series circuit, you can specify just one current to register and everything else is known. Fine. But instead of that, so you can do this here. So, or you can place external probes also. So let me just show you that. So if you right click probes, so you'll have voltage probes. So everything will be measured with respect to ground. So let me just choose that. So this is the voltage probe, and you can just place it anywhere, but everything will be measured with respect to ground. Fine. So when I place it here, it will measure this VC. If I place it here, it will measure as LC voltage or this voltage, one with respect to ground. So we want this, so I'll just place it here. And if you just double click on this probe, it is actually a polyphase block. So you can always specify to till 26 phases, like whatever number you want, you can specify. Fine. Why you require 26? Because in power electronic circuit, you'll require a lot of gating circuits and a lot of logical circuits. So you'll require this kind of a bus kind of creation, like you have multiple signals you can interface. Fine. We'll come to that later sometime. So let me just select one phase and say okay. Fine. And so this is done. And if you want to add current source, yeah, current measurement, go to this, right click and probe current. So you have here this feature. So let me just cut. So current placements are like cutting wire kind of technique. Fine. So you need to cut the circuit, place the meter, because we don't have clamp on here, fine. So you need to do this. Yeah, so having done this, and again you have 3 nodes here, but let me just show you. When you double click, you have an option called current node. So you can use this current to some calculation or some other circuit later, but we don't want it. We want to make it simple. So let's say okay, yeah, that's it. So it just gives you current in this direction and this voltage VC, in fact. Yeah, and the switch is imbibed within this switch. The source here, it's 0. Just keep this in mind, fine. If you start with -1, you will not see any transient, so to speak. But if you start with 0, the switch is the source is started at 0, fine. Yeah, in fact, if you look into the switching thing, you have a controlled switch here, but it's actually require more specification to it. For example, you need to specify what is the current order of current levels it will be interrupting, like something like circuit breaker. So it becomes not really useful for this kind of simple transients, fine. So here you can always use this, or maybe I'll show you something, some better switches, fine. For example, where it went, this kind of switches which are much better. I'll show you that. We'll at the end maybe we'll show you that. So the circuit is ready, everything is ready. So yeah, so that's it. So circuit is ready now. So we need to just do these simulation settings now. So you want to perform time domain simulations. Yeah, so till here are we comfortable? Have we drawn this? Yeah, please help me out.
Can you please repeat the current and voltage measurements from where you got?
Yeah, see, it's actually, if you right click in the canvas, you will have this probe, the top section probe, and when you click on probe voltage, you will get this voltage probe. Similarly, for currents, you will have this one, the where it went, current probe current. See?
Okay.
Yeah, and the settings are very simple. Actually, you just double click and you have only one phase, and don't add any nodes to begin with. Let's say okay. So this is the current probe, in fact, a meter. Yeah, and same for voltage also. That's it. Yeah, so we have saved it. So I hope if you are doing it, it will be well and good, because it's a hands-on right now, and later on we'll switch to demonstration mode, just showing you the capabilities and some nuts and bolts of this tool. Yeah, so I assume, like, we'll wait for some few more seconds if you require time to make it. Yeah, and in fact, if you want to show some values, let's say if you want to show what is the resistance value, you can always, let's say, click and you can write label, like it's 10 ohm, so you just say 10 ohm and you will come here. So if you want to change some settings for this, you can always do in this. You click on that, then right click and blah blah, like a lot of beautify thing you can do it over here. Same for inductance, source, and everything. So label, you can just label it. Yeah, so we assume like you have done this much, and now let's go to the setting part. So just to begin with, so delta t is the step size. So let's begin with, let's say, 10 microsecond kind of order, because dynamics we are already comfortable with. These are LCs. L is like 63.3 millihenry, and capacitor is 10 microfarad. So it's very common example we have seen most of the time. So it has actually a resonant mode of 200 hertz, around 200 hertz. So 10 micro should be more than enough, in fact, fine. Just to show you, I'm just choosing this randomly, fine, but you should not do that. So yeah, let me just go with that. So I'll just specify it as 110e minus 3, 10e minus 6. Yeah, so it's like 10 microsecond kind of order. Or if you want let me just make it 100 micro, no worries. Yeah, 100 microseconds, and you want simulation to, let's say, 0.1 seconds, and rest other parameters, let's not worry. So this frequency also won't matter unless you are doing some other kind of study. So in time domain it won't matter at all. Yeah, so I hope you are done with this circuit drawing, circuit settings, and simulation settings. So in more or less in PSCAD and other tools also, you have this kind of steps: build the circuit, set the values, then set the simulation parameters. Yeah, so shall we move ahead?
Yes, yes.
Yeah, having done this, see, yeah, I'll just show you some more things after some time. Yeah, so once you're done, we have built this circuit for first time, so it's good to make an ATP file first. So we'll go to sub process and make ATP file, and let's not change the name, and we'll just save it in the default directory. Yeah, and having done that, we'll just run the ATP file. So what happens is, if you had noticed earlier, like if you save the file, it gets saved as .acp. It's ATP circuit program or circuit part or something like that. Fine. Excuse me. Yeah, so its ACP file is this actually circuit file, and then when you say ATP file, like the ATP file, like let me just show you what, when you have saved this ATP file, how it looks like. So there is a tab called edit ATP file. So these are nuts and bolts things. Fine. So I'm just showing you for just completeness. So in fact, originally you had to write this kind of script and pass it to the ATP program. Fine. But in ATPDraw you can do this kind of circuit making. And when you, if you notice, actually when I say make ATP, what it does is, in fact, looking at the diagram, it just creates a lot of nodes and which elements are connected and what are the values. So it's just like parsing. When you say make ATP here, it just parses the circuit and gets the value in some number form wherein I can access using some code. So this is the thing. Fine. So here these are some simulation settings here. If you read, actually if you read through, so this is the idea. So these are some nodes, and if you see, there are R, L, C parameters. So it's 10 ohm resistance, C is 10 farad microfarad, and this inductor is 63, and this is connected between these two nodes. Fine. And then you have a capacitor with some initial value and some measuring tools. Fine. So all those things. Fine. So that's what I'm saying. So it just parses it. So there is no mystery in this. Again, like you, when you make a circuit, you parse it, get the values, and you simulate it. So it's done every tool, in fact. Fine. So having done this, we have created ATP file. So let's run and see what happens. So when you run, so it solves all the dynamic equation pertaining to step size and the circuit using this step size, and it just gives you some values. So we have 2 meters, voltage and current. So it just gives you voltage and current, and you don't have you didn't invoke any other internal measurements. Fine. Yeah, so when you do that, so let me just show you what is the voltage and current. So when you just plot, so these are the waveform. So fine. So since the current is very small, so it's not visible, so let me just scale it with 100 times. So in this plot xy tool, actually you have a factor element, you can just add. So I'll just say plot. See, you get this plot. In fact, if you match it, you can just do some kind of judgment. Fine. So let me just zoom in the initial part. Yeah, see, the red is the voltage here. Which voltage? Of course, we mean actually this capacitor voltage. This probe measure with respect to ground. Fine. So in fact, this is capacitor voltage, and initial voltage, it starts with 0, isn't it? 3 volts, isn't it? And this is the inductor current, which starts with 0. Fine. So initial condition matches, and if you measure this oscillation stuffs, so it's of the order of, actually if you measure, it will be around 200 hertz. Fine. If you want to note what is the value, actually this tool helps you out. So if you click down here, there is a button called like the marker kind of thing. So you get this line, and you can just measure each and every voltage. Fine. Like measurement. So you can measure what is the voltage. So you can note here, actually, okay, this is the time here, and this is the time here, and difference of that and inverse it, you will get the frequency, approx frequency of the mode for that, mode for this setting. Fine. And that's it. So, and if you want to do steady state checks, so VC is this, the red one, and IL is this. So for capacitor, current leads. Fine. So it leads this, so it makes sense. Fine. So it's, in a way, you can claim it to be correct. Fine, provided you have sufficient step size and all this chota checks. Yeah. So that's it. Like you have done a simple first, like hello world kind of circuit making in this tool. So I hope you have done this. Fine. So this was hands-on. So any doubts or any query you have? Yeah. Yes. Let me show you. It was just like just a minimal fraction, like what all things capabilities it has. So just to show you like how it works. Yeah. And for example, when you, so the plotting thing we have done. So in case if you want to see plot again, so how to do? So there are buttons here. So to run, make ATP and run. So this was the tab, fine. This funnel and then this electricity, like lightning kind of symbol here. This is compile and run. So it parses the circuit, parsing and execution, fine. And this is for plotting. So let me just open that plot again. See, you can open it. But again, see, there is a six digit node. How much digit? Yeah, 6 digit node. So it's a limitation to that. So like node name will always be in 6 digits here. So why I'm saying this, because I'll show you something more. So see, these values may not make sense to you. Okay, what is this node, where it is, I don't know. So you can always go and specify that. So if you remember, I mentioned you, if you right click on a node, okay, I overlapped something. Yeah, let me just take this probe out, and if I just click on this probe node, I can always specify a node name. So let me just say it as VC. Okay, so it will get highlighted as red color, fine. And now I'll place it over here in this node. So what will happen is all this node here will be assigned as VC, name as VC, and this node, let me assign it as IL. Okay, let me just take it out, right click in the part, and I'll just say I capital L. See, this is now red. So in a way you will get a clue. Okay, this is the IL, means this current one. If you have complicated circuit, let me just show you after some time what is so-called complicated circuits, right? I'll just show you if you want. So this demarcations, it helps. And in case if you want to see what is the name, so you can just click on name on screen, so you can see this node name. And similarly for this, so for huge circuits, this will be very handy, fine. And in fact, this, the moment you assign this things here, you can use it in some other calculations also. Like for example, you can do some mathematical tools, like a processing or RMS value calculation or some kind of control. You can do that just by assigning this, fine. So let me just compile and run again. So when I hit compile and run, now in measurement you will see, okay, voltage VC and current IL. So one node you have specified, so it just picks that node. See, these are the things. And just to do scaling, I'll just do 100 here. That's it. So this is the basic hello world kind of program. Yeah, so any doubts or anything so far? Yes, no, maybe. Yeah. Hello, am I alive? Hello.
Yeah, Santosh, we can hear you.
Yeah, yeah. So I think things are simple, isn't it? Yeah, so if you have done it, it's well and good. If not, so we'll be sending you the recordings. You can just look at it, because now we'll switch to a demonstration mode wherein we'll just show you a lot of functionalities we already know, fine. So idea is we'll explore. Actually, our aim is to explore the tool, and whatever we know, we'll just fit in that tool and see how it works, fine. So let me just go to a new circuit, so to speak. So this is the simple example. Yeah, so let me close this and let me create another file, fine. So I'll just click on new. So what we'll do is now we'll consider this example. Yeah, where it went, I think it's here. Okay, I messed up, it's here. So the transmission line examples will pick up a very simple one, this kind of element, fine. And we'll just compare with our program, like how it works. So we'll do for this simple pair, or if you want me to pick up some other, I will do that. Fine. So yeah, just to begin with, let me just show you this simple circuit. So we'll just patch this circuit, fine. So you already know, like this source and switching we can always imbibe within one block in ATP, because it becomes easy. You need not specify any current interruption levels like real circuit breakers, fine. So we'll just make this. So we have a line, a step signal, step DC, and open circuit end here, fine, whose values are this. So let me just keep it in this workspace, and let me move to original workspace here. Okay, I am in original workspace. Yeah. So to build it, let me just show you what all models are available in this tool. So if I right click in this part, yeah, yeah, if we do that, so yeah, I'm sorry for distraction. Yeah, I just got distracted for some moment. Yeah, so if you see lines and cables, actually you have various settings, fine. So what sir have already told you, I'll just show you, but we'll work with very simple models to just illustrate. and maybe later on you can just explore. Well, let me tell you, this is very handy tool to do a lot of complicated things. Fine, let me just show you that. So for simple thing, what we have given in assignment, these are categorized within these two subsets, fine, distributed elements and lumped elements. So if you go to distributed element, wherein you have Bergeron model, which is also called Lee-Clark's model, fine, Clark's model, you can just explore sometime. So if you go here and it's a single phase circuit, is it? So you can just always say single phase. So yeah, see, I'm sorry to call transmission line as a circuit, but truly speaking, it's a circuit, fine, modeled here as a circuit. Yeah, so you get this. Yeah, let me centralize it and hit plus button. So you'll see a two node kind of element wherein you have this illustrative distributive element LC's thing, fine. So when you double click over it, you'll get this kind of functionality. So you have lengths, outputs, inline, like what all parameters you can specify. If I say L dash C dash, you can specify those. If I say Z and V, propagation and characteristic impedance, you can specify that. Or if you want Z and tau, which is, I hope you can relate to, fine. So you can specify these things. And if you want conductance, like G to be included in this simplified model, you can include that, like proportional to some constant values. Just note, if you say this, actually G, if you make 0 and R externally, you attach to this Bergeron model, fine. Bergeron model is an exact model for a lossless transmission line. Just as a reminder, R actually gets attached as an external model. So you can experiment, in fact. For example, you specify a circuit, a parameter to this like line. Let me just switch to L dash C dash because we already have that data. So I can specify L dash C dash and R to be 0 to begin with, let's say. And but transmission line has a resistance, let's say aggregate resistance of 1 ohm for this 300 kilometers. So I can always write 300 ohms here, or I can attach it externally, fine. And you can just compare those two models just to see how it works, fine. So in fact, this will be more or less like that, more or less like the same thing, and same goes with the conductance as well. Yeah, so without more ado, let me just show you this first help file because it will be required to know in case if you don't know what all things to be specified. Same thing with the inductor and capacitor definitions here. Like if you make this X opt and C opt option, like X option and C option to be 0, you need to specify everything in actuals, like what you have already seen in the assignment or in general discussions, right? But here if you specify like some frequency value, like some value, you will get in ohm meter or Siemens per meter, something like that, fine. And yeah, so these are some definitions, what they call as propagation speed, which you already know, we are comfortable with, isn't it? Fine. So yeah, so without ado, let me just pick the values which are there in this. Excuse me. Yeah, this becomes much handy to switch, isn't it? Yeah, so this is 1 millihenry per kilometer, fine. And if I come here, it's asking me details in millihenry per meter. So what should be the value here? So 1 millihenry per kilometer, fine. So if I make it meter, it will be 1 micro, actually 1 microhenry, or 10 to power minus 3 millihenry. So I'll put that. In fact, you can write here the exponent way of defining a number, fine. So you can always write 1e minus 3. So it's like 1 millihenry, fine, like 1 microhenry per meter kind of thing. Same with the capacitor. If you come here, it's 12 nanofarad per kilometer, fine. So yeah, the calculation things and those conversion things, I have already done that. So if you come here, it's asking you everything in microfarad per meter, fine. So what will be this value here? 12 nanofarad per kilometer. If you convert to micro, what it will be? Yeah,
12 picofarad.
12 picofarad per meter, fine. So here it's asking in microfarad, so I'll write it as 12e minus 6. So now it's like 12e minus 6 and micro, it's like 12 picofarad per meter, fine. And then length is in meter, fine. So when I was trying to illustrate, actually blindly I had put 300, like 3000 kind of, or 300 kind of thing, but I hope you won't make the same mistake. It's like 300 kilometers, fine. So I had some weird responses, like it was the speed was way beyond certain limits, fine. So it's like 300 kilometers. and no output as such we want, and we'll just say okay, that's it. So this is the simple definition of this. Oops, I'm sorry, I have a very bad habit of always pressing Ctrl S every second now and then. Fine. Yeah, let me just show you what all what other models are there. Fine, maybe we may not come again to look this, having done all kind of simulation and analysis. So in lump, when you come the distributed thing, you have transposed, like untransposed lines, the transposed lines in the sense which says like balance, everything is balanced. But for single phase, things are straightforward. This transposedness, the like how to put it, like when you have a multiple, a matrix for an inductor, let's say 2 by 2, 3 by 3, there you will have feature of this transposition thing coming up. Fine. But for single phase, you don't have any meaning of transposition as such, because it's the only thing in the universe. That's our notion of building it. So transposed line for single phase, it doesn't have any meaning. Yeah. And when you go to untransposed Casey-Lee model, you have only 2 phase and 3 phase models here. Same if you go to lumped models, these are like RLC pi equivalent here, which is what we have given in the assignment, like single phase RLC kind of pi equivalent. So R, again, if you happen, let me just show you. So if this is a lumped model in pi lump model, so let me open it. So it will ask you in the same idea, R, what is the resistance, inductor and capacitance. Fine. So we don't require this. I'll delete this. Yeah, in fact, I think it will give you better picture. So lumped, you have this, and you have advanced one, which is RL coupled thing. So you can do a lot of coupling business of various elements over using this tool. So let me now just show you that. So let me just show you one element. So it goes like this. So for a single phase, you don't have any meaning of mutual coupling. Fine. But for if you go for, let's say, lumped, then a coupled thing, but for 2 phase, you'll have some kind of coupling definitions coming up. Fine. So what is R22, what is R21, and here you assume to be symmetry. Fine. So you need to specify for a 2 cross 2 matrix, you need to specify three elements as such. Fine. Because of symmetry and nature, like nature of the definitions how we use, actually it will come out to be symmetry, like R11, R21, R22, and L11, L21, and L22. Fine. So this kind of mutualness, you can always use this model actually for any. In fact, if you go to this mutual conductor numerical here, in fact, you can always realize this using this transmission line model. It doesn't matter. Fine. Where it went. In fact, for a lot of other elements, you always use this kind of abstracts. Where it went. Yeah, lumped, RL, and this coupled thing. Fine. Single phase or like 2 phase, you can say one branch will be for the bottom one and for this, and then you can just play with it. Sorry, it's cold here. Yeah. So this is the line thing here, which is the Bergeron model. If you I hope you things are clear, isn't it? It's nothing great here. So 300 kilometers, 300 into 10 to power 3. Yeah. And then this definitions here. And now we'll just construct this circuit quickly. So what all elements you require for where it went, this circuit. So what else you want?
Source only.
Yes, in fact, yeah. So switch, you can place it here. For the idea is we want to just observe VR. Fine. So we can change the place of a switch. It doesn't matter, but we'll keep things in series. So switch I'll just absorb in this source. Fine. Again, I'm saying why to do that, because it has some redundant data. If you use a circuit breaker definition, you need to specify what order of current you need to interrupt. Fine. You don't want any other dynamics to be coming up. So you just want a step sine wave and a series resistance. So let us do that. Fine. So we'll go to source, AC source here. So it will look very weird. Control R to rotate when I double click, and just let me just choose some value. Fine. Let me just assign the same value. So it's 200 root. Yeah, let me just keep it as 200 right now for time being. Fine. 200 volts line to. Yeah. So yeah, 200 volts. Fine. To begin with, 50 hertz instead of that we want 60 hertz. And just to start, because we want transient, that switching element, we will replace this -1 with 0. Fine. Just bear with it. Fine. A lot of mistakes happen here. So if you want transient, you start with 0, or if you don't want, you just start with -1, like steady state, but then you need to add a switch with some more definitions. Yeah, then voltage, single phase, line to ground, and grounded. Okay, so switch and things are modeled here. Let me just make it a little big. I can do this always. fine, and then a register element, so linear, and then go to register here. That's it. Yeah, one more thing which will bug you, like this comes with experience again, is like in case if you want to move this branch, so how to do that? So you need to come and just like normal click, like left click, long pressed, so you can move these branches as well. Fine. In fact, there is some rubber kind of option in this tool, so I can choose a node and I can move it anywhere. Fine. So just to connect. Fine. So long press, and I can use this rubber band feature kind of tool, which is very handy. Fine. I have not seen any other tool with this feature or similar feature. Fine. So this is done. Yeah, and this here it's open circuit, so always you can place a register if you want very high, or since it's a model like much better in this context right now, so we'll just keep it open circuit. Fine. So we'll just place a voltage probe, and just before setting we'll just set it to single phase, and we'll just ensure like it's single phase. You can just place it over here. Fine. And we want to measure the input also, so I'll just copy this and paste, and I'll just measure it here. So like input, I'm just saying exact input voltage, or in fact this will be measurement for what is the voltage applied to the this RL, the complete circuit. Fine. So let me just tell you again. So the circuit what I have built, it's not one-to-one correspondence. Fine. Till I require only a open circuit voltage and the source voltage here, Vs. If I ask you what is the sending end voltage here in the transmission line, you need to model that switch thing. Fine. So it won't give you correct, because there will be some kind of current dynamics happening, and this drop will be added in this register. So what it means is you need to keep it here if you want to measure what is the input. Yeah, the sending end voltage, but this is the source voltage. Fine. So now I am saving it, so I'll just say simple Berg model. So I just saved it. Settings we need to check. So setting is like 100. Yeah, it's 10 ohm, I guess. We'll just select that. Yep, it is 10 ohm. Source is 10 ohm, and it's some voltage. Let's not worry about what this is. We'll just concentrate on the frequency and the pattern. Yeah, this is done. Yeah, so let's quickly run and see what happens. Yeah, so how to do that? So first the simulation setting we need to do. So what is the simulation setting? So just to begin with, we'll just specify it as 1 micro, but in the simulation it's given you to use some particular value. Fine, which is like tau by 10 times, like tau times like 10%. How to put it? Yeah, 10% of the tau value which is available to this transmission line model. Yeah, so instead of that I'll just choose to begin with. Fine, 1 microsecond. I think it's good enough to begin with, but you should not blindly specify this deltas and t's. Fine, and the interest will be, let's say, 0.02 seconds, and I'll just save it. First run, you can always say make ATP file, save, and then you can hit run button here, run ATP. So the moment it runs, it gives you 2 voltages, and now you don't know which voltage correspond to what. Fine, so we can just specify this also. So you can just right click over here, and you can say VR, or let me just say REC, receiving end, and name on screen, and this is sending end. It's not sending end, it's actually source. So let me just say SOR. If I save and run again, so there is a tab. If I hit and run, you'll have receiving and then source. So if you plot it, say this is the nature you will get. Yeah, so that's it. So let me just increase the time span so that it looks better. So I've just increased the time span to 0.2 second, like 10 more cycles. So this is the waveform what we obtain here. Does it look similar? Like, is it an alien waveform or it's a known waveform? What do you feel? Hello? Yeah, I hope I'm. Hello? Yeah, is it audible, sir?
It's audible. It's audible.
So these are actually the known tools, like which like we already had discussed in the assignment 4. So, and maybe you have done it already. So I think it should be comfortable, isn't it? And just note, these are not, yeah, even if you try to make a sense out of it whether steady state is correct or not, so it goes like this. So source is little lesser than what the receiving side is. Why? Because of the mainly you can call it as a Ferranti effect, though you have a source resistance, but it really doesn't matter here, right? Because at then whatever voltage you impress here, because the current will be negligible which comes through, so the receiving side will be higher than the source side for this 300 kilometer and this specifications what you have done. Yeah. And for example, if you want to just relate, because yeah, let me just show you, if you want to relate this with the already known waveform, a simulation experiment. I hope you have received this file. So if I run this, how to do, if I run this, so we'll see this kind of waveform always here. So magnitudes, let's not worry. I hope it looks similar, isn't it? But the red one, let's not worry about it. So the source is coming here and the blue one is actually the waveform, fine. The open circuit Bergeron model voltage. Yeah, if you see here also you have the same waveform. So if you want, I'll just show you how to load this file there or that file here, fine. Yeah, so let's do that. If you want, I'll just show you quickly. See, the voltages, what is there, it actually gets generated in .pl4 format, fine. Some format which is native to mainly to this ATPDraw, pl4 .plot file, pl4. So you need to select this and you just need to say export, fine. And let me just choose desktop to do that exporting, and I'll choose this MATLAB 4 version. This MATLAB is it has some nomenclature issues, so we'll just go with MATLAB 4. Let's not worry what it is right now. And I'll just say, so what was the circuit? It was AC, source resistance, then Bergeron model, and then open circuit. So I'm just showing you a way of naming it, fine. So this was the circuit, and no spaces allowed. So I'll just say this and just save it. So it just says, okay, your variables have been exported. So let me just close it. So this is the variable which is exported, fine. So I'll just pick this variable, copy it, and take to the this file here in the directory of the Octave, fine. Yeah, I think I can't open this here, so let me just go there. Where it is, extra materials. I'm sorry to, actually I opened it, I think I closed again. Solutions here. Yeah. So what I have done is I just placed the mat file here, so just so that I just want to see the blue curve and this, fine. So let me just kill it here, run it. So you had the exact model thing, fine, and then this one, the Bergeron model thing. So let me just load it here itself. So I hope you can track. So instead of picking things here, so let me just open the original file, which is P6 here, P6, fine. So this was the circuit, and below I'll just plot these things, plot the things, fine. So let me just run it again. So this was the original thing, fine, which we did with simulation. So since we have chosen the voltage there as 200, so let me change it appropriately here, fine. So we just set it as 200 volts there, isn't it? So we are just choosing this to be 200, and let me remove the kilovolt thing, 200 volts, fine. And rest all is same except the time constant. So maybe we have chosen microsecond, here it's like of the order of milliseconds, fine. So let me just run it. So this is the order of things we obtain using simulation, our code, our understanding. And now let me just load the mat file which we exported from ATPDraw, this one, what do you call ATP, yeah. I'm sorry, yeah, so I chose this load option here, load button. So I'll just copy it here. Actually MATLAB, you get those tab hitting features, and I'm really very comfortable using those tab feature. When you write a name and you hit a tab, you just get it. But in Octave only, it seems it just works in the command prompt, like in here in the console, not in the editor, fine. So yeah, so when I save it here, so let me just pause everything here and just see what all variables are available with this. So let me say, I don't know if these things make sense. So what I'm calling is, I'm just looking at what all variables we got from Octave. So I'm just opening this file. So we get t, verec and vsor, right? So since you have originally you have this, yeah, let me remove this thing, plot it, hold this, and then use this variables t and this. So I'll just simply call paste. So we have this variables, isn't it? V receiving side. So we want to plot that against this. So we'll just call it as VREC. So what it is, V capital REC. V capital REC, and we'll call this in red color. Yeah. So it's in blue color and this is in red color. And let's hope it works. So when we call this, we'll get this kind of waveform. Yeah. I'm sorry if it is not really visible all right or perfectly to you, but I hope it makes sense, isn't it? Yeah, sorry, is it visible?
Yes, yes.
Yeah. So
Yes.
so the moral of story is, what we are doing, it's not like anything we are doing. It's like whatever we do, actually these are also imbibed in this commercial software. Fine. And let me just correct myself, like the tool which we are using right now or stating you or demonstrating you, it's a free, like royalty free software, but it doesn't mean you can use it at your will. Fine, there are some associated license. Yeah, so this is the idea. Fine, so whatever you simulate, it doesn't diverge so much, but the difference what you see here, can you help me why it's happening? Yeah, it's merely due to the step size. Fine, step size here in the R code, it's of the order of like 0.1 millisecond. Fine, and here we have chosen 1 microsecond of the order of that. Fine, if you want, let me just set that. Fine, so let me just do this. So 0 into this and just make 1e minus 6 plus. This is just so that my program doesn't get destroyed, so I can remove this 0 and yeah, we are back to square one, something like that. Yeah, so if I run this, hopefully eventually it should be more or less the same. Yeah, it is. Yeah, it's still running. Fine. See, the running time for this, again, it depends on like lot of things, because we have initialized lot of variables here to begin with. Fine. It was written in a way so that it just gives an idea, okay, how to write. Fine. So yeah, so this is the thing. Okay, let me yeah, maybe the settings what we have done here, I think it may not directly pick up because it's not an integral multiple, and this may not suit the definitions what you have done here. Fine, so instead let me just show you that when we do in ATP with this very same step size which is there here, this one, and let me just see what is the value of h we get. So this is the value of h. So let me just copy this step size there. So long G, when I say h, so this is the step size. So let me just copy this, go to ATP and set this as the step size. So this we can do it easily because our program may require modifications to suit. So I'll just paste that step size here, 0.2, save it, run once. So here, run it, just export. I hope you can track, isn't it? It's straightforward. So we'll go to desktop, place, and we want to just in desktop. I'm sorry if it messes up, but this will make things clear. In fact, whatever we are doing in the assignment, things are really exactly the same. We do it in like this commercial packages. Yeah, so we have exported it. So I'll just copy this, go to the folder here and paste it. Yep. Done. Minimize, and we'll just run it and see if it works. Yeah, is it fine now?
Yes.
Yeah, so I hope you believe it. Fine. So idea is in the sense, like we know, we believe it, but things go exactly the same way we model it in this very script file. So instead, to just to compare, fine. So let me just show you this just to compare. So if I open this, take this circuit to this window, and if I just do this justice, yeah, both are exactly same. Yeah, so this code written here with the like ideas and this model which is implemented in this software, both are exactly same, fine. So this is the takeaway thing, fine. So we know it. So what I do, since we have invested too much time here, but on the way you got to know, okay, how to export, how to compare things here, and what all the settings you need to make, fine. So let me not invest more time on comparing the results. I hope you believe it, fine. So I'll just show you some more things with this, and then we'll conclude in few minutes. Yeah. So this is the thing here. So let me zoom in. Yeah, so this was the circuit, fine. Yeah, and then the other thing is the lump thing. I think you can already make it, but yeah, so what I'll do is I have already prepared those circuits, fine. So I'll just show you, open it, copy it in this window, and just run and show you, fine, because it's just a matter of constructing it, fine. It should not take much time. So let me just open that. Oops, what is the shortcut? Yeah, control open directly this. Yeah, so I just made some, I was just playing with this tool just to explain you some things. Okay, so there are some more attributes if you require. See, this is very pinch of a salt in a bowl, something like that, fine. A lot of things are there to be covered, but I think it will give you a good gist, fine. So we have seen just now this idea, like this circuit, and its counterpart here, which we asked in assignment, was this. So let me just copy it, fine. Window, you just tile it horizontal the way you want. Fine, and this was the lumped counterpart of this. So let me just remove this switch here and use this switch, because the settings what you have done, it will pertain to this thing. Yeah, so I'll just zoom in here. So this was the circuit. Now, so yeah, so one more thing, like few more stuffs, like maybe it may help you out directly. So this is the L, C's and R. So if you see, the L value is 150 millihenry, which is evidently this. It went. The L value, like it's 1 millihenry for 300 kilometer, fine, like per kilometer, and if you do that, it will be 300 millihenry. But when you do this kind of equivalency, it will come out as 150, and same goes with C, which is around 3.6 micro, I guess. Yeah, 3.6 microfarad. Yeah. So yeah, so for example, if you want to just see this, so how to demark this voltage and this voltage, you already know that. See, everything is same, fine. 10 ohms and voltage is also, since we copied it, no need to show you the setting, but just for sake of completeness, we do that. Yeah, here actually, instead of placing it here, logically we feel even if you place voltmeter here, it should not hamper, isn't it? But let's keep things as it is. So I'll just call this as receiving end underscore lumped. So I'll just say REC underscore L. Just keep in note, try to choose node name not more than 4 or 5 letters, fine. Especially for 3-phase, polyphase things we have not yet seen, but I'll just show you if time permits, or maybe in advanced section we can take it sometime, fine. So it is sending in lumped, send lump. I hope things make simple, isn't it? Things are very straightforward here, very straightforward. That's it. So let me just run and see. So if we run using this very same step size, let's see what happens. So we have source or send L, like both are exactly the same and same thing, in fact. Yeah, actually there is a current source coming up because I think I have invoked the current measurement here, fine. So you can see currents also. Yeah, I hope I'm audible.
Yes.
Yeah. So yeah, I forgot what to do. Yeah, so yeah, receiving, I'll just show you. So source side is common to both, isn't it? So this one, and receiving in Bergeron model and receiving in the lump model. So let's compare. Fine, so it's too dense. So what I'll do is I'll just remove the source. I'll just click here, so it just vanishes. And if I say update, so this happens. So this is the kind of waveform you get using that lumped model. And if you compare with the already sent file, or in the sense the code file here, this one, let me just remove this. How to remove? Control R. Yeah, Control R works. Yeah, so a lot of settings we changed it, so it may come up like this. Okay, yeah, see plot 6, since I have modified it, it's picking some other value, fine. So but I hope it makes sense, fine. So let me just remove it if you want it to be complete, fine. Return, that's it. Now it's original in the sense as the way it was. I hope whatever small changes we do here, you can track easily, fine. Okay, so now what is this? Okay, lumped model also you need to change the setting. So I'll just do one comparison and then we'll wind up for the day maybe. Fine, it's 200 into and remove this kilovolt thing. Come back. It was written in a way to show you, fine. So yeah, so that's it. So see, for example, if you just compare, like it will be same, isn't it? We have just discussed that, isn't it? So that's it. So this is the result. So if you see there is no delay for the lumped model, like the access, there is no transport delay, so it just starts. Here also it just starts, fine. That's it. So idea is whatever we code and do in an assignment, in a way you are building a package, fine. If you do it and just think in a way, so that's the idea. And for example, you don't want to look at this circuit which is already verified. You have verified it and it works, you know it, but just to save time, because it runs pretty straightforward, fine. Just remind me, like in conclusion I'll show you a circuit which takes me a few minutes to solve it, fine. So what you can do is you can just hide it. So you right click, select an entity, hide, and then click on hide button. So it will just go gray, like in gray color, which implies it's not really participating in the circuit simulation. So when you run it, it will be pretty straight, like fast, and you can see only variables associated with that. And just for interest, let me just show you this current, how it looks. So this is the wave shape of current, fine. You can just check sometime. So yeah, so this is the idea, yeah. So now what else? Okay, so we got the idea, and now for example, if you want to submit a report or you want to show some fancy things or some results, prior results, one can always play with the settings here. For example, if I right click on the canvas and say add an object, see you have a lot of other things. For example, if I draw a circle and if I say okay, so this is the transmission line model, so if I click here, see I can place it here. So okay, so this is the transmission line model, right? So all those chota like beautify thing, you can do it. So that's the idea. And if I want to place some let's say a picture of the waveform, what results I got it when I simulated, so you can just save it as a picture here. And let me just open the result, click some results, plot, fine. And there is an option here, if you just go lower, so you have some save variables and plot copy option, fine. So I'll just say copy, so it says okay, plots are copied, fine. So I can just double click and paste, in fact any diagram or any notes also, and if I say okay, it just gets generated. So in this version, this is the best part which I like, is this, you can do all this kind of signatures, so to speak. Like I need not run this simulation, you can just run it and show the typical result how it looks. And one good thing about naming the node is this, in fact even if you just pass this, I'm just saying it's small simple things, fine, which is very cumbersome if you have thousands of this plots, fine. We'll maybe sometime later we'll show you. See, this comes here, we receiving lumped and sending lumped, so it gives you a signature, okay, this is the way, fine. So that's the idea. There are factor things, and maybe if you want to compare some waveforms, you can just do this load button, and you can load any other files also. Maybe in the advanced section sometime we'll see that. Yeah, and just few more things I want to show you. And first, mainly the frequency models of transmission line and the other thing, which may be useful. Maybe from Monday he may not touch upon, but he have already touched actually. So let me just show you what all settings are available in involved models or frequency dependent of this kind of models, fine. So we have already seen this lumped and distributed thing. Yeah, so any doubts so far? I'm sorry I didn't ask. I think it's simple, straightforward, isn't it? Yeah. Hello.
Yeah.
Thank you. Yeah, so I'll just show you, just we won't simulate because it's really not easy to build that model like in right front of in few minutes, fine. You'll require a lot of data, fine. So let me just show you. So if I go to LCC template. This is the beast of transmission model in this tool. Fine, believe me, it's very popularly used tool in a lot of literature. Fine, so this is the thing. You have a lot of things to be set here. So if you just double click over here, you will have if not 100, like tens of settings, fine, to be done. I'm sorry. Yeah, so idea is actually this is the major tool which is mainly used for 3-phase, but you can always downgrade or upgrade 6-phase, 10-phase, 20-phase, and so on and so forth. So where it happens, for example, if you have a transmission tower with 2 circuits or 4 circuits going together, so you need to build that appropriately. So when you say a single tower, like transmission tower, you have only one circuit. One circuit means combination of an R phase, Y phase, and B phase, or ABC phases. But in the other side, you will have always another phase, ABC. So that will become double circuit. So you need to assign this as 6-phase, fine, and so on and so forth. So these settings maybe we'll see later sometime, but let me just show you what all features you have. So over here, like you have features for including core cable, like enclosed pipe, some configurations of this transmission model. Overhead line are the specialty here. Then transposition feature, if you want, you can make it. And see, when you say it says individual circuits, actually it implies like in the tower whether you have multiple double circuit, single circuit, and so on and so forth. But since we want only one circuit, you can just, so ideally you can transpose each circuit independently, or you can do multiple circuits also. Then auto bundling, this is a bundling feature which will be helpful while entering the data. I'll show you that. Skin effect, segmented ground, if you select that, you need to add some more features. And then real transformation matrix. So if you remember, like the coupled circuit L and C is for 3-phase. It was a full matrix, fine, though symmetric but full matrix, like L11, L2, L12, L23, and blah blah. So just to do some model fits and things, you can force the matrix, the transformation matrix. So I hope it makes sense, fine. So you can force it to be a real, like you can choose that matrix to be real, and you transform and you get the results, fine. And then in options here, you have this Bergeron model which doesn't require as such any other data. See, all the resistances, distances you can specify here, and rho is actually for the mainly ohm, it's ohm meter, fine, it's for ground. So it generally, as a thumb rule, it's taken as 100 ohm meter. And all the settings pertaining to L dash, C dash, actually this engine, actually LCC engine, just a second. Yeah, so this setting, actually this engine LCC routine here, it's very powerful, fine, in the sense let me just show you what I mean. So when you come to data here, actually you can add any number of, see, all the elements what you specify. For example, we have a tower, and at the top you have a ground wire, and then you have a 3-wire like R phase and Y phase and B phase. Let me just quickly just show you. So it's like R phase, Y phase, and B phase, and within this R phase you have, let's say, 4 conductors or 4 conductors, yeah. And then you have a ground wire like this, and then you have a ground structure, like all structure distances, dimensions you need to specify, structural dimensions, fine. So what is the height of this conductor, like all the conductors you need to specify. So in that way I'm saying it's a beast, like you can do any kind of tower dimensioning and things here, and it will calculate and give you what is the coupling inductance calculated, so to speak, what is theoretical inductances, capacitances, and so on and so forth, fine. So let me come back. So you need to specify for each and every conductor, you need to specify, and just bear in mind one very important thing is, like, see, for example, if I choose a model LCC, let's say I say this is a Bergeron model, but here you don't have any kind of difference in the sense a distance feature, it's just modeled as a length of line, fine. But in reality, what's true is, like, instead of having a 300 kilometers line Bergeron or a transmission line model, you try to chunk it into few kilometers, wherein it's more or less proper, fine. What I mean is, you have a 2 towers. It's a very important thing which is not clear when you read manuals. It's this. So if you come here back in the settings, it specify what is the tower height of that conductor. Let's say I say first phase is, let's say it's a ground conductor, second conductor is a R phase first conductor, then Y phase first conductor, and so on and so forth. So you need to specify what is the tower height, or at what height it is located. So you need to specify that. And V mid is also specified, actually between 2 towers, what is the what is the middle, like the sagging happens, like what is the distance of the length happening, like this one, this we made, you need to specify actually for each conductor. In fact, just remember, if you have let's say this one, and then this 3 phase and 4 subconductors, so you have 13 conductors, fine. So yeah, just excuse call, yeah, I'm sorry. Yeah, so for all 13 conductors you need to specify these dimensions, like this what is the tower height at the tower, what is the height it's located at, and when it is in mid somewhere it will be lower, isn't it? So for example, this for see why I'm specifying, because maybe it may not be really required to take another session specially for this, so just to indicate you, fine. So this is the R phase conductor, but when you see in mid it will be somewhere here at this height, fine. Earlier it was here, now it is here. So you need to specify all those kind of configurations. So it's always good to have, let's say you have 100 towers in a true system, like in actual system you have 100 towers, so at least model 5 or 10 towers to begin with, so you'll have more exact kind of capture, like a practical capture, fine. So I'm just giving an idea, fine. Maybe a sample file will pass it to you, you can just explore. It's giving some issue, but yeah, I hope you these are some definitions, fine. Let's not worry about it right at the moment. Oops. Yeah, so let me come back here. So you can specify all those kind of intricacies, and then if you go for pi kind of model, or let's say JMRT, which is frequency, so these 3 are actually the frequency dependent model, fine. So if I select pi, like it's again like it's assumes something and then model it. JMRT, NODA and Semilin, all these are frequency dependent models, so you need to specify actually. See, ideas actually need not specify what is L, capacitance and mutual things. Everything will be getting specified by this data, the dimension thing, what I just told you. So this engine, what it takes input as the actual dimensions, very important. The actual dimensions will go into this LCC routine, and it will throw you, like it will give you the coupling, inductances, capacitances, resistance, and all kind of field phenomena as well. Not all, but few major important things, fine, like wave propagation and all those things. So here, like JMRT, what it says, so what is the order, like what yeah, how to put it, so what is the, yeah, in a way it has a subroutine which calculates order automatically, but you need to specify till what range you want to model this. So you say, okay, I want 6 decades, means 6 tenths of frequencies, and how many points you want to estimate for, like fit you want to do at what frequencies, and so on and so forth. So and fine. So and what is the starting frequency, and what is the steady state frequency eventually you'll end at, and so on and so forth. And you can always say default fitting, so all these settings will vanish, else you need to specify all these kind of settings, fine. I hope sir have already told you this, we may not have touched upon this in lecture, but you can just explore in simulation and see how it affects, in fact. I'm sorry. And same thing goes with NODA and Semlin also. So there are some minor differences what NODA and like different, these are some nomenclatures, fine. Like people who worked on this area, the model they named as it is. So these are things, fine. So I hope it makes sense when sir had told you like what all kind of frequency fits. So what frequency fits, when we say it goes like this. So whatever points in the interest of frequency range what you have specified, at every point this calculations of L dash, C dash and R dash will be done. That's it does, fine. So it just models that mutual, like the elements, the matrices L, C and R, G, those matrices it builds on and it uses for appropriately. So it's a engine, LCC engine, like a coupled line engine which does this, all this jugaad thing. Yeah, and since it is 3 phase, let me just show you. If I just drag it, you will see a thick kind of conductor. So always you just pull it apart anywhere, it will be thick. It implies it's a 3 conductor, and it, in fact, if you click on one part, you will see it says okay, 3 conductors are available, and so on and so forth. So what we'll do is, I think it will go unbound. So this 3 phase thing, maybe when topic comes up, we'll just explore again. Yeah, and yeah, that's it. And just one more phenomena, if you feel, I'll just show you. I hope it's simple, isn't it, to track? Yeah, or maybe not that simple. Yeah, but let me just show you some things which we already know, fine. Yeah, see, there are a lot of chota like tools and features of this we may not have touched upon, but we may take it later sometime. See, this is the switch actually which I told you. It's one of the switch which is easily controlled. So it's like you control it from other source. So that's what we do, and it's the same capacitor thing. Initial voltage you specify, and when you do this simulation, so you observe some kind of numerical oscillations, right? So that's what it does. So it's modeled in trapezoid. So if you do this, let's say current, yeah, so initial bump it's like 100 kiloamperes depending on what is the resistance value. Oops, what I did. Okay, so step size is actually 10 to power minus 4 in the assignments. So these are the things which we obtain. I don't know how if it is really visible. See, again the modeling thing is the how you model it, and since we have used switch which is pertaining some other block module of ATP, it introduces some kind of maybe some modeling differences from our program. So what happens is in the voltage chatter, if you see there will be a chattering effect. Let me zoom in. Sorry to put it like this, but it's really visible in the current wave shapes. See here. So there is actually a chatter effect happening in the voltage depending on what is the value of R and things we choose. But in the current, if you see, it's really visible here. But the current actually eventually it should have for this this circuit, in fact, it should have died down. Fine. It's a simple R is negligible and C with 10 volts, and it should get connected to the other capacitor of the same magnitude. So current actually it oscillates from 1 ampere to -1 and so on, and it continues forever. Fine. So this is what numerical oscillations are, and it generally happen when you have a voltage interruption, like for a capacitor when you have a sudden change in a voltage kind of interruption, and for an inductor when you have some kind of current interruption, like quick current change, maybe when you open circuit it, or when you do this kind of, let me just show you. Fine, when I run this you'll see this current. Fine, so this RL and this voltage, let's not worry. So the current, when you see for a simple diode circuit which is just like a switch, again you will get this kind of chattering effect. In fact, you should not have got this. It should have been like very small bump, or maybe you should not have any bump as such. Fine, yeah, no bumps as such, but here you get this kind of chattering, and if you measure the time step, it will eventually come out to be the step size. So it's not like inherent to the circuit, but it's due to the numerical oscillations, which will be maybe again covered up in the upcoming sessions. Fine. So question is like how you avoid it or how to handle this. Fine. So mainly it happens with the dynamic elements like RLCs, and whichever, for example, the for inductor it's L di by dt. So for di, like if di by dt's are held to, it should not be infinite. Fine, that's all. So for voltage also, the voltage, if you try to finite it somehow, you can remove this. Fine. So one way of doing is you reduce this. Reducing this, and there is some kind of feature like called damping feature, which exactly what it does is actually it adds a resistance in parallel to an inductor. Fine. So for example, if I specify some damping effect, so you will see a small bump which is coming parallel into the inductor. So what it does, current won't be interrupted at all in this. So let me just run this again and show you, convince you for the very same step size. So this is numerically handled. Fine. So it just, you'll get simple or small, very small bumps coming up, but eventually it's much better than the cleaner, in fact cleaner in a way. Other ways of handling is you don't do this, you make it zero, no damping, because these circuit solutions may change slightly. And same goes with capacitance as well. For example, if I just invoke the damping feature here, it will come in series. So series capacitor, like some resistive element will come up, whose magnitude are calculated as shown in the help file. You can just see. So eventually it will come to some time constant times of, you want to add a time constant to the response. Fine, it just comes to that. When I run it again, you will see this at least the what do you call the this will reduce, the chattering effect will be reduced. Fine. So this is the capacitive currents. So I hope you can see this. So it eventually dies down. Fine. It takes around 3 or 4 milliseconds depending on what damping I have set there. it just dies down till 6 milliseconds. It just dies down. So, but in a way, it just quenches it. Fine, quenches in the sense eventually it dies down. That's the idea. But earlier we had a sustained kind of numerical oscillations. Fine. So that's it. So this is one way, or another way is to add some resistances, or you reduce this step size to a greater extent, and then you may escape this oscillation stops. Yeah, so I think it's good time to stop unless you have any doubts or queries. Yeah, I think it may be too much content for today, maybe, or may not be. Yeah, please help me out. So if you have any queries, please help, or please ask. Yeah, Kausa sir.
I don't have any doubt now, but in case I do have, I'll get back because
Yeah, please ma'am, please, we are here to help you. So if you have any small chota doubt also, please ask, get it clarified instead of investing hours of things to do. Yeah. Just before concluding, I just want to show you what are the circuits we call as complicated. Fine, so let me just show you one. Is it there or is it left? Oh, it's there. Okay, it's not that complicated, simple. Okay, yeah, let's take that. It's one level of complication, but it's not that complicated. But yeah, it will give you a feel, maybe. Fine. So this is the circuit. So each box you what you see, this is our LCC, the three-phase transmission. Yeah, let me just show you here. Maybe you may appreciate this, how these actual settings are done. You have to sit with a lot of data. See, these are the data, and if you want to see how the tower looks, there is a tool view. So this is how the tower looks. I don't know if you can see this. Oops. See, this is the tower things. I hope you can see now. So there are two ground conductors here. Come on. Okay, it's not there. I'm sorry, but you cannot see that. But here it's like you have a ground plane here, and in the center you have like this R phase, Y phase, and B phase with 4 conductors and 2 ground lines, right? Which corresponds to this setting. So ground lines you always specify with 0, and 1 phase, 2 phase, 3 phase. When you see the bundling thing, it is already connected, and you can name something, and when you say OK, it will create a small file which you require to run it. Fine. So these are some definitions. That's it. And length of this line is 290 kilometers, and so on and so forth. So it's just something. Fine. Let's not worry what it is. So you have all these kind of things, and then you have transformer like dynamics model, like which is really complicated at this moment. Fine. Let me just tell you, at this moment it seems to be complicated, but it's fantastic. Fine. And see, a lot of things you can add. In fact, I hope you can understand the time it takes to build this kind of circuit. Right? So a lot of chota things are there, and you get some mapping functions by just pressing Control M. So you can just bird view, like as a bird you fly and you look at the circuit. That's the way. So what I'm saying is, it gives you a good grip, and it's like mostly acceptable, like the results are acceptable kind. Fine, it's verified kind of thing. So this is the circuit. In fact, if you just lubricate and just show you in a page, it goes like this. This is a page, around 50 to 30 buses, and you get some elements, lot of dynamic elements, and that's it. Yeah. Oh, I thought I closed the Chrome. Yeah, so that's it from my side. If you have anything to add, sir, you can add, or if you have any doubts, please let us know. Yeah, ma'am.
nothing as of now.
Yeah, sure. Manohar, do you have any doubt? I think it should be simple, isn't it? Yeah, Deepika and Imran, any doubts or anything you want to ask?
No doubt till now.
Yeah.
Thank you.
Yeah, Imran, it seems you have some doubt. Yeah, I think you are not audible here. anyway, I think it should be good enough. So if you have any doubts, please approach us, and maybe later, based on your interest and maybe some more elements, if sir wants, we'll have another session for advanced tools. Fine. Yeah, Imran. Yeah, I think that's it then. So we'll conclude for the day. Sir, Kaustav sir, do you have anything to add or comment?
No, I think it is sufficient. So the main takeaway lesson of this session should be like to believe that what you are doing indeed is actually very similar to what the softwares also do in the background. So Santosh had verified it with the MATLAB program that what we found from the system model that the results should come out. Actually, the simulation softwares do nothing else than that. And it gives eventually the same results. And therefore, this should motivate you to not use commercial softwares, but rather believe that people like you and me should also be capable of doing these simulations on our own.
Yeah.
So that's, I guess, was the main motivation that we wanted to show by the use of these softwares. And we hope that this comes useful for you in the not only in this course, but even after this course when you keep on working in these aspects.
Yeah.
And you make use of these ideas when you encounter such issues regarding numerical simulations. I think that's okay.
Yeah. Sure. So we'll wind up for the day. And if you have any queries, please let us know. Fine. The recordings will make it available by evening, today night. And if you have any doubts, you can look at it once more. Yeah. So I'm stopping the record.